Hi everyone, welcome to today's webinar, How to Evaluate Color on Small and Odd-Shaped Plastic Samples. Presenting today is Tim Mao, our Applications Engineering and Technical Support Manager at X-Rite Pantone. I'm Robert Grotan, a Global Digital Learning Manager, and I'll be moderating today's webinar. Just a few things to go over before we get started. Due to the number of people that are attending today's webinar, we will keep everyone muted. If you have any questions during today's presentation, please feel free to use the questions function on the GoToWebinar panel, and we will have some time to answer a few of your questions at the end of this presentation. This webinar will also be recorded, and we will follow up with an email at the end of this webinar with a link to this recording so that you can watch it again. So with that, I will turn it over to Tim to kick things off.
Thank you, Robert, and welcome everyone. Let's dive right in. As you can see on the screen, we're going to talk about how to evaluate color on small and odd-shaped samples, or phrased in another way, measuring things that have maybe been unmeasurable in the past. So let's dive in. So our intro and our agenda, we're going to talk a bit about the limitation of traditional devices, traditional spectrophotometers. And then we're going to talk about how the MetaVue VS3200 overcomes those limitations. Talk about presenting the sample to the device, targeting, capturing a precise measurement spot, evaluating the measurement, and maintaining an audit trail. And while we are indeed focused this webinar somewhat on plastics, everything we're talking about applies regardless of the material. If we're talking about something that's unmeasurable because of its size, its dimensions, its makeup, and so on. So we'll get into that a little deeper. So let's move ahead. So traditional spectrophotometers, they're best suited to measure flat samples. You can see here we have a benchtop spectrophotometer, a nice flat panel going in to measure it. In some cases, in plastics, you might be producing something that has no flat surfaces or areas that are measurable, and it may require you to mold a coupon, right? A little flat plastic piece that gets molded along with your product so that you have something to measure and test. Well, that's waste. That's creating something for the sole purpose of being able to measure the color of it. And a coupon doesn't always reflect what the actual product looks like. So that's an issue. Second issue with traditional spectrophotometers is that the sample must fill the aperture. So here we're looking at an image of a 25 millimeter, in this case, aperture on a benchtop, and put something in there that's a stripe. Well, that instrument's going to average all of that together. It's not going to measure white, and it's not going to measure green. It's going to measure a mixture of white and green all averaged together. So I don't have the ability to measure the smaller green area or the larger white area separately with that aperture. I might be able to do it with a smaller aperture, but in some cases my sample can't fill the aperture. That's an issue. Traditional spectrophotometers, the instrument and the sample have to be in contact with one another. Otherwise you have light leakage, and that creates all kinds of problems with your measurement. And lastly, positioning odd-shaped samples can be difficult. So here we got a picture of a handheld instrument, for example, measuring a flat piece of wood. But then if I need to go measure that other piece of wood with a profile on it, yeah, it might be flat on the top, but it's going to be kind of difficult to balance the instrument on there and get a good measurement of that. So traditional spectrophotometers, again, they struggle with that, measuring things that are beyond that. Now we have ways of trying to address that in some cases with rigs and jigs and a variety of things to try and work around those limitations. But what we're going to talk about now is a device that gets past some of those limitations. So this is a picture of a MetaVue VS3200. Okay, it's a non-contact, so the instrument does not touch the device, the sample. And it's an imaging spectrophotometer, and those two things will be very important, and we'll see why in just a moment. It also typically involves a stand, this adjustable stand. As you can see, it's got a little crank on the top there, so I can actually raise and lower the instrument to allow me to put different sized samples in there. If I want to measure something flat, that's fairly flat, right, I can lower it way down. If I want to measure something that's of a significant size, I can raise it up, and I can adjust that stand to properly position the instrument on the sample. Here's an example of that. Excuse me. This is actually a set of headphones, and we are aligned to measure a color that's on the side of one of the ear covers on those headphones. So we all know roughly how big a set of headphones is. We can raise the stand up to measure that. Here's another picture where we're measuring that pink plastic on those ski goggles. Okay. Another difficult sample to measure there, right? It's not really flat. It's got curvature. It's not terribly thick. It's not going to be easy to present that pink plastic to a traditional spectrophotometer. With a stand, I can adjust it to the correct height, get the sample inside, and then using this imaging spectrophotometer, I have the ability to go ahead and do measurement. We also have then in the software, and we're going to go in and see a demo of the software here as part of this webinar, the ability to do on-screen targeting. So this is actually the targeting in the software for the image on the right, where the headphones are. So those headphones on the outside have a little green area that we want to measure, and so I have the ability to see the entire area and to target, as you can see with the little circle and the crosshairs, where in there I'm going to measure. So I can say, I just want to measure that part of the green spot and obtain color data for that. Okay, so that's kind of high level. Now, let me just walk through a couple more bullet points and we'll jump over to actually looking at the software and seeing how we can use it. Okay, so we're going to use the device connected to IQC iMatch software. It's our quality control. That's the IQC software. You can also do formulation with it. So if we need to measure something and generate a recipe, we have software to do that. Same instrument connecting to both pieces of software. And we're going to do a live demo to show you targeting and capturing a very precise measurement spot, evaluating the measurements, maintaining an audit trail. And just so you're aware of what we're looking at, we're going to go in and see a bunch of already measured data as well as look at doing some measurements. We're going to see a red, a green, and a yellow measurements that I did previously, and it was the red, green, and yellow buttons on these two game controllers. Okay? One of them happens to be purple, one of them happens to be yellow, but we're talking about the buttons and being able to measure those. So I will toggle over here to the software, and you should now be seeing our IQC quality control software looking at some measurements I did of the yellow button, for example. So those measurements coming into the QC software, I've got, everything from visually expressing the color, where the color standards in the middle here, and these are my 7 samples around it. You can see a varying color. I've got my delta values, right? I've got pass and fail, either in words or in color. I've got LAB plots. Let me expand that a second. And I can even do things like looking at it 3-dimensionally to actually see my tolerance and where the dots are of the samples that I measured. So won't spend too much time doing the QC part because that's really, we have other webinars, quite honestly, you could see to talk about this software. But what's unique is we've got the ability, just like we would with every other, let's call them standard kind of device, to get the measurements in here. But what's unique is the ability to see what we're going to measure when we're going to measure it. Now I've got the same, I'll switch here and show you, here's the red button with its variation, okay? And back to the yellow. because I want to show you something else. We are capturing, when we do this measurement, and I'm going to change this view to show you the image. So now I can actually see on that yellow button where I measured, okay? So this lighter area, that larger diameter, that's the full illumination. The maximum size it could measure is 12 millimeters. These happen to be down to, I don't recall, but I can look. The software will even tell me, oops, here, that I measured that with a 3 millimeter area, okay? So I can see what size area was measured. So I was using 3 millimeter area here when I was measuring. Now we've got a sample, number 6, with a pretty high delta E, 3.98. Well, sample number 6, if we look where the area of measurement was, it actually kind of went off the edge of the button. And so it's measuring this recessed area, right? That image gives me a clue as to why this one failed. Now, there are some others that failed as well, but they're much closer to the color standard and maybe they're okay. But, you know, why do I got one 4 delta E? We actually was an issue with where we took the measurement. And if you can see, there are also a couple of little dots, flaws on that button that got measured in as well, okay? So this image capture helps me, helps me track what specific things might have happened. It's an audit trail to see what was measured, okay? So that the ability to audit that, and this is saved with every measurement. So we can go back and see why did it fail? Did we measure in the wrong area? Did we happen to measure where there's a flaw or something in the product? I also, by the way, have the ability to do something here. I actually measured this green button twice. You can see full size, 12 millimeter, but you can see in the image, you can see that there's an A, right? That's because that green button is the A button for the game, right? It's kind of embossed into that plastic. So in addition to controlling the size of the measurement, I also have the ability to use something called smart spot, right? Or a smart measurement. Normal is going to work that it averaged all the color together inside this circle, okay? Smart is going to take all of that measurement and it's going to smartly, hence its name, remove any artifacts, we'll call them, right? Might be highlights or shadows that are in there. So it's literally going to eliminate the color of that A that's embossed in there. And that's why I get this kind of a color difference, because I didn't move it or anything, and yet I still have almost a 0.7 difference in color, because the smart eliminated the pixels that are a different color because of the shadow of that A. So this is something that this instrument provides to us, those two abilities. Now, I want to give you a view of what we're talking about to actually do a measurement. So I'm going to turn on my instrument here, like I'm going to take a trial measurement. You'll see it's just black underneath it. Okay, I need to lower my instrument a little bit, and you'll see what I'm going to put underneath there is something that you will all be very familiar with. That's a die, right? From my Yahtzee game. So there's the dice. If I wanted to measure that dot, and I'm using this simply because it's something we're all familiar with its size, I could zoom down all the way to 2 millimeter. Maybe I can get away with 3. And then I can point and click, and it's now going to just measure the color inside there. Now, with the color of this die, with all those funny little spots in there, I probably want to use the smart part of it as well so that it eliminates those things. Since this one has a little bit more than that one, I'd get a very different result if I leave it in normal mode. If I put it in spot mode, it would clean them both up to compare just the black part. Okay, let me give you another example as I slide that out. about how we can deal with things of some very small sizes. Roll it down even further. That is my cell phone charge cord. Everybody's familiar with how big those are. And again, we can go, we could drag it down to 2 millimeters. It's curved, of course, but I'm able to get into a spot there that I can get a very repeatable measurement on a sample that's pretty tough to measure in any other means. The thickness of that cell phone cord, the ability for me to do that, and if I wanted to measure it, I would just type in a name and hit next and let it go ahead and take the measurement. I'm not going to do that at this point because I got one more thing I want to show you. Let me just crank this up. I'm going to put one last thing in here. This may not be quite as familiar, but I think it's a fabulous example. So what I'm putting in now is a USB to serial adapter. And it, like lots of things I might connect, has a little green light that'll come on. And you can see I happen to get lucky there. Let me lower this a little bit. Get it right there. So that is an LED that happens to light up, right? But I could actually go to a 3 millimeter spot, I think. Might be able to get lucky. 2 might be safer. Zero in a little bit. And measure the color of that teeny tiny little plastic cover, because maybe it matters that we get the color of that right. So some very difficult things. This is, of course, it's one of those little, like I say, little lights, things that lights up when there's power to it. And so it's not flat at all. It's very circular. But I can get a very repeatable measurement with this device because I can zero in on the exact location that I need to measure. I can save the color information. I save the image so I know where I measured. And, if the next time I put it in there, it goes in like that. Now I need to measure it again. Oh, just point click, move over. The whole point click part is really, really the key here for us to be able to do this kind of measurement. So hopefully this helps you see and understand how I can use the capabilities of this device to zero in on the right size measurement, point and click to the right location to measure, and store that audit trail to be able to view the results that I get with that device. So we're going to click back over here to our PowerPoint and move into our Q&A session. But before I start answering questions you all have put forward, I think Robert has a poll he wants to bring up.
Yep. So I'll bring that up right now. So if you do have a question you would like us to answer, feel free to submit those now while we wait for questions to come in. If you would like to have someone reach out to us, if you'd like to talk to a sales representative, feel free to answer this poll question. And we'll leave that up while we wait for your questions to come in.
All right, so I see a question here. Someone asked, since I didn't take any measurements, how long does it take to take a measurement? Well, it does take longer than a standard spectrophotometer. It's just under 8 seconds. Okay. And the reason it takes longer is it's an imaging spectrophotometer. And the reason we can do those things like zero in, point and click is we're literally generating a spectral curve per pixel. And so when we identify the region of interest, the area, if you will, that we're measuring, it's then going to bring those reflectances that are for those pixels together to do it. So it does take a little longer. It's not as fast as a typical flash the light, capture all of the light that bounces, right? We've got a lot more data to process, okay? So there's that. Second question that I see about how repeatable are the measurements on the USB charging cable. Well, I've done, just measure the same spot, move it, put it back. Of course, it's a cable, so it's long. It's kind of hard to get. But we're talking about, a half a delta E or less. If I were to force it to make sure I'm always measuring the exact same spot on the cable so that I'm sure there isn't any actual color difference between it, it's even smaller than that, right? The instrument itself is a something like a 0.15 repeatability, average DE across tiles on it. So it's very, very repeatable. Another question was, what geometry is the VS3200? It is a 45-0 device. So while the other instruments that we showed when we were talking about traditional instruments happen to be sphere instruments, the same is true about the flatness of the sample and the difficulty measuring small things with 45-0 devices. This instrument, the MetaVue VS3200, is a 45-0 geometry device. And so for some of you, you may be thinking, well, if I'm traditionally using a sphere, then will this agree? No, it is going to see color differently, but it also has the ability to be able to measure, for example, everything you see on the screen there. Some wheels from a skateboard and those goggles and, the game controllers and the cords on the game controllers, every button on that game controller could be measured, even the little teeny tiny gray ones. Even the ones on the tops and the sides. We're measuring buttons on remote controls because we can get down that small. So it's opening up this world of getting to measuring these things that are very difficult to measure in other scenarios, if not impossible. Last question I got is, does this take gloss out of the equation? So a 45-0 geometry instrument, by its very definition, right, sees a gloss difference as a color difference. So if I were measuring whatever sample of whatever size and it was identical in color and then there was a very big gloss difference, it's going to see, the instrument would report that as a color difference because the light in a 45-0 instrument is coming in at a defined angle of 45 degrees, a glossy sample is going to reflect a lot of light away from the optics, and a matte sample won't deflect nearly as much light away. So more reflectance comes back, if you will. So a glossy sample by this instrument will always be seen as darker than a low gloss sample of the same color. And so it does interpret gloss difference as a color difference, but that's a good thing if you're looking at all of these objects and kinds of things we're talking about measuring. The consumer also sees those as color differences if their gloss is different, right? It's a visual thing. So those are the questions that I saw. Thank you for those. Appreciate all of your participation. If you have other questions that come up later, you're more than welcome to submit them. We will get back to anybody who we were unable to respond to in our time today, but we have reached the end of our time. And so I thank you all. Robert, back to you.
Yep. Thank you, everyone. We will do our best to follow up with any outstanding questions. And again, this recording will be sent out to you as well tomorrow. So thank you for joining and have a great rest of your day.